Hello students, welcome back to my channel. This is Nipa Patel from the Math Masters, and today we are going to do next few questions of chapter 1 Relations and Functions exercise 1.1. Please like the video and subscribe to get the notifications for new and upcoming videos. Let's get to it.
Question 9. Show that each of the relation R in the set A equals x belongs to Z, where 0 less than equal to x less than equal to 12, given by 1. When R is equal to A comma B, where mode of A minus B is a multiple of 4. And second question you are given that relation R is equal to A comma B, where A is equal to B. And we need to show each of these are equivalence relation and find the set of all elements related to 1 in each case. So we are going to do question 1 first, and then after that we'll start doing second. So let's do this relation first. What are you given? Your set A is every integer from 0 to 12, including 0 to 12, right? So let me just rewrite that A. A is your number in that integer from 0 to 12 and including 0 and 12. Now relation that you are given in this question 1, first we are doing this question, just question 1, okay, and relation you are given here is A comma B, where mode of A minus B is a multiple of 4. Now since we need to show that it is an equivalence relation, that means we are going to show that it is reflexive, it is symmetric, it is transitive. So let's start with reflexive. Now definition of reflexive is what? That A comma A belongs to R for every A belongs to A. Now let x comma x belongs to R. So if x comma x belongs to R and your rule to belong to R is what? Mode of A minus B is a multiple of 4. So that means mode of x minus x, that should be a multiple of 4. Is that a multiple of 4? X minus x going to be 0. So 0 is a multiple of 4. Yeah, of course. 4 times 0 is going to be 0. Right? So 0 is a multiple of 4. That means x comma x belongs to R, and that means A comma A belongs to R, and hence it is reflexive. So R is reflexive. Now we are going to start symmetric. Now definition of symmetric relation is what? That if you have A comma B belongs to R, then you must have B comma A belongs to R. Let x comma y belongs to R. Now if x comma y belongs to R, that means mode of x minus y is a multiple of 4. Now if I change this sequence a little bit, if I take negative out in common, then y minus x I can write, right? So is a multiple of 4. Of course it is a multiple of 4, right? Still the same difference. It is in that mode and it is actually the same. So negative of y minus x is going to be mode of negative of y minus x is going to be y minus x, right? Or I can even write this way, is a multiple of 4, and this means y comma x belongs to R, and that means b comma a belongs to R, and hence R is symmetric. So R is symmetric. We are supposed to show that this is an equivalence relation, so we need to show that it is transitive as well. So now we are going to start working on transitive. Now definition of transitive is what? That let's say you have a comma b in R and you have b comma c in R. That means you must have a comma c in R. So this is the definition of transitive. Now let x comma y belongs to R and y comma z belongs to R. Okay, we are taking a equals x, b equals y and c equals z. Now if xy belongs to R, that means this means that mode of x minus y is a multiple of 4, is a multiple of 4. And if y comma z belongs to R, that means mode of y minus z is a multiple of 4, right? Multiple of 4. Now, since mode of x minus y is a multiple of 4, I can rewrite that like this, that x minus y is equal to, first I'm going to write like this, so it's little less confusing for you. So, mode of x minus y is equal to 4 times, let's say constant m. And same way here, that mode of y minus z is equal to some constant times 4, so 4n. Now, if I get rid of that mode sign, then I can write what? That x minus y equals plus minus 4m and y minus z equals plus minus 4n. That's how we get rid of the absolute sign, right? That's how we get rid of the mode. Now we want to find the relation between a and c, and in this case x and z. So to find the relation between x and z, we need to eliminate y. And how do we eliminate? We just need to add these two equations. So if you add these two equations, you are going to get what? X minus y plus y minus z is equal to plus minus 4m plus minus 4n. So y and y is going to cancel out. So you will have x minus z equals plus minus 4. I'm going to take out in the common and then m plus n inside the parenthesis. So actually this is nothing but what? That I can show like this as well. Mode of x minus z is equal to 4 times m plus n. So it is nothing but what? Multiple of 4. Why? Because 4 times some constant. And as soon as I show that, this implies that x comma z belongs to R, and that means a comma c belongs to R. That's what it has to be a transitive relation. So R is transitive. Now I don't have space here, so I'm going to write here on the top. So it was reflexive, it was symmetric. See, it is reflexive, it was symmetric, and it was transitive. So it is all three. So we can say that hence relation R is an equivalence relation. Why it is an equivalence relation? Because it was reflexive, it was symmetric, and it was transitive. So when a relation is all three, then that relation is called equivalence relation. So we showed that what we were supposed to. But now we need to do what? Find the set of all elements related to 1 in each case. So right now we are doing this case 1. So for this case, we need to find the set of all elements related to 1. That means equivalence class of 1. In other words, they are asking us what? Equivalence class of 1 they are asking. Now always remember, when you are asked equivalence class, you just need to imagine that number, whatever number you are asked. Here we are asked for 1. So whatever number you are asked, that number is your second number. So wherever you see B, you are going to write 1. So this is going to become what? A comma 1. See, A comma B. So A comma 1, wherever you see that second number, that B, you are going to write 1. And mode of a minus 1 is multiple of 4, is multiple of 4. Now we are given A equals all the numbers from 0 to 12, all integers, not all the numbers, but yeah, all the integers from 0 to 12. And from that 0 to 12, you need to find all the possible numbers where a minus 1 is multiple of 4. Okay, so let me write here a. So a is what? 1 comma 2, sorry, not 1, it starts from 0. So 0 1 2 keeps on going until 12, and equivalence class of 1. Now a minus 1 must be multiple of 4. We don't worry about negative or positive because we have that mode sign around that a minus 1. So 1 minus 1, 0. Yeah, 0 is a multiple of 4. So it is going to be what? One of the possible number is 1 because 1 minus 1 is 0. Now 5. 5 minus 1 is 4. 4 is a multiple of 4. Then 9. 9 minus 1 is 8. 8 is a multiple of 4. And I close that parenthesis before even trying. Why? Because if you are going to try to look for another number, it's not going to be there in your A, right? Because 9, see this 1 to 5, 5 to 9, it is like 4 jump. So 9 plus 4, it's going to be 13, and we don't have 13 in that set. See, the highest number is 12. So 12 minus 4, sorry, 12 minus 1 will not be a multiple of 4. So it won't be in our class. So this much. 1 comma 5 comma 9, this is our answer for this part, that find the set of elements. These are the set of elements of equivalence class 1, or which are related to 1. Now we are going to do that question 2. First let me just erase this part. Okay, now let's start this second question. Again same thing, we are given this a, all integers from 0 to 12. This relation you are given, r equals a comma b, where a is equal to b. We need to show it is an equivalence relation, and after that we need to find the set of all elements related to 1. Okay, so now we are doing this second part. One we already finished. So now second part, a set you are given as all the integers from 0. So 0, 1, 2, 3, so on till 12, and the relation you are given is between AB, where A is equal to B. Now since we need to show that it is an equivalence relation, we are going to work through all those three: reflexive, symmetric and transitive. So let's start with reflexive. Now definition of reflexive is what? That A comma A belongs to R for every A belongs to A. Now let A equals X, or let X belongs to A. So that means X comma X belongs to A. That's what we need to show. So if X belongs to A, and from this condition A is equal to B, so this means X is equal to X. And since X is equal to X, that means X comma X is going to belong to A. And that means A comma A is it's going to belong to A, and that means R is reflexive, right? What we were supposed to show, that A comma A belongs to R. Now the relation itself is what? A equals B. So if you take A equals X, then X comma X must belong to A. And see, X equals X, right? X, if X comma X belongs to A, then X must be equal to X, and that is true. X is equal to X. So that means A comma A is going to belong to A. So that means R is reflexive. Now we are going to start working on symmetric. Now definition of symmetric is what? That if A comma B belongs to R, that means you must have B comma A belongs to R. And for this, let X comma Y belongs to R. Now if X comma Y belongs to R, that means X must that means X must be equal to Y. Why? Because that's what the condition is there in the relation A equals B. So if xy belongs to R, then x must be equal to y. And since x is equal to y, I can write y is equal to x. And since y is equal to x, y comma x can also belong to R, right? So I can say that b comma a also belongs to R. And since b comma a belongs to R, then R is symmetric. Okay, so we proved or we showed that it is reflexive. We showed that it is symmetric. Now we need to just work on transitive. Now definition of transitive is what? So if you got a comma b in R and you got b comma c in R, then you must have a comma c in R. So let x y belongs to R and let y z belongs to R. Now if xy belongs to R, that means from that condition a equals b, x must be equal to y, right? So if xy belongs to R, that means x equals y. And if y comma z belongs to R, that means y is equal to z. So if x is equal to y and y is equal to z, that means yeah, we can say x is equal to z, right? And if x is equal to z, that means from that condition looks like x comma z will also belong to R. And if x comma z belongs to R, then a and c. So a comma c belongs to R because our x was a, z was c. And as soon as we showed that a c belongs to R and a c belongs to R, that means we proved that it is transitive as well. So R is transitive. So R was all three. See, we proved first that R is reflexive, then we showed R is symmetric, and then we showed R is transitive. And since it is all three, we are going to write what? Hence, R is an equivalence relation. R is an equivalence relation. Now the second part of the question was what? That we just need to show that, and after that find the set of all elements related to 1. Find set of all elements which are related to 1. So let me just rewrite that part. So A was 0, 1, 2, 3 and so on till 12, and our R was a comma b where a is equal to b. So we got this two things. We just proved that it is an equivalence relation, and now we need to find equivalence class of 1. When you are asked to find this thing, that set of all elements related to 1, that means you are asked to find the equivalence class of 1. So equivalence class of 1 we can write this way. So equivalence class of 1 or elements elements related to 1, they are going to be this. What did I say in that earlier question? That wherever you see B, you are going to plug in 1. So equivalence class of 1 is going to be, I am just rewriting this, but instead of B, wherever I see B, I am going to write 1. So A comma 1 where A is equal to 1. So we will have how many elements? Just 1, right? So this is going to give us just 1. Why? Because A must be equal to 1. So it is going to be 1 comma 1. So it's going to be just that element 1. So we will have the set of all elements related to 1 is this 1. This is our answer. Question 10. Give an example of a relation which is 1. Symmetric but neither reflexive nor transitive. So for this one, we need to give possible A set and possible R set. So let's take 1, 2, 3 in A, and then it must be symmetric but not reflexive and not transitive. So 1, 2 and 2, 1. So if our relation set is this, if our R set is this, then 1, 2 is there and 2, 1 is also there. So it is symmetric. But it doesn't have 1, 1, 2, 2 or 3, 3. So it is not reflexive. And 1, 2 is there, 2, 1 is there. So 2, 2 in common. So we must have 1, comma 1, then and then it is transitive. So we don't have 1 and 1, so it is not transitive either. So this is the example for that question 1. For number 2, it must be transitive, but neither reflexive nor symmetric. Okay, so let's again take the same A, 1, 2, and 3, and this time it must be transitive. So let's take 1, comma 2, then 2, comma 3, and since I took that and must be transitive, so it must have 1, comma 3 as well. Okay, so this is transitive, right? Why? Because you are given 1, comma 2 in R, you have 2, comma 3 in R, they both have 2 in common, so we must have 1, comma 3, which we do, so this is transitive. Now it cannot be reflexive, so 1, 1, 2, 2, 3, 3 we cannot see here, so it is not reflexive. Symmetric, we got 1, comma 2, do we have 2, comma 1? No, so it is not symmetric either. So this is the example for that question 2. Now question 3. So for that 3, it must be reflexive and symmetric, but not transitive. So let's again take same A, 1, 2, 3, and in our R set, this time we will have many elements because it must be reflexive and it must be symmetric. Since it has to be reflexive, so those elements are going to be there 1, 1, 2, 2, 3, 3, because if you have all this, then and then it makes it reflexive, right? Now it must be symmetric as well. So if I write 1, 2, I must have 2, 1. Then if I write 2, 3, then I must have 3, 2. Why? Because it is symmetric as well. So if you have 1, 2, you must have 2, 1. If you have 2, 3, you must have 3, 2, right? So this is symmetric also, but transitive. So see here, look for here that you got 3, comma 2 here, and you got 2, comma 1 here. So in 3, comma 2 and 2, comma 1, this 2 is in common both of them. So you must have 3, comma 1 in your relations, then and then it is transitive. We don't have 3, comma 1. See, can you see 3, comma 1 in here? Nope. So this is reflexive, this is symmetric, but this is not transitive. So this is the example for that question 3. Now we'll do this question 4. Now in that 4, you are supposed to give example such a way that it is reflexive and transitive but not symmetric. Okay, so it has to be reflexive, it has to be transitive but not symmetric. Again, let's take that same A, so 1, 2, 3, and in R, since it has to be reflexive, so 1, 1 must be there, 2, 2 must be there, 3, 3 must be there, and it must be transitive as well. So let me just add one of them and I think it will be enough. So 1, 1, 2, 2, 3, 3 is there, so yeah, it is reflexive. Now let's check for transitive because it must be transitive as well. So we got 1, 1, we got 1, comma 2, 1 in both of them, so we must have 1, comma 2, which already we have, right? 1, comma 2. So yeah, it is transitive and it cannot be symmetric. So since we have 1, comma 2, we must have 2, comma 1, then and then it is symmetric. We don't have 2, comma 1, so it is not symmetric. So this is the example for that question 4. Now we'll do this question 5. Again for 5a, we can take the same 1, 2, 3, and this time it must be symmetric and transitive but not reflexive. So we cannot take all of those 1, 1, 2, 2, 3, 3. Why? Because it is not reflexive. So how about take 1, 1, then 1, 2, and 2, 1. Okay, so symmetric. If you have 1, 1, the other way around 1, 1, we have that. If you have 1, 2, other way around is 2, 1, we have that. If you have 2 1, then other way around is 1 2. We have that. So yeah, it is symmetric. Now transitive. This both have 1 1 in common. So 1 comma 2. We must have 1 comma 2, which we already have 1 comma 2. Now these two have 2 2 in common. That means we must have 1 comma 1 in here. We already have. So this is transitive as well. And it is not reflexive. Why? Because just getting 1 comma 1 in relation, it does not make it reflexive. You must have all the a which are in your set A, that you must have a comma a. So like, if you have 1, you must have 1 comma 1, then you still have 2 in that, so you must have 2 2 here. We don't have that. We have 3 in our set A, we don't have 3 3 in here, so this is not reflexive. By seeing 1 comma 1, we cannot say that it is reflexive. Why? Because for all the a's in this A, we must have a comma a. So we cannot see 2 comma 2, we cannot see 3 comma 3, so it is not reflexive. This is the example for that, number 5. Question 11. Show that the relation R in the set A of points in a plane given by R equals P comma Q, distance of the point P from the origin is same as the distance of the point Q from the origin, and that relation is an equivalence relation that we are supposed to show. Further, show that the set of all points related to a point P which is not equal to origin is the circle passing through P with origin as center. Okay, so first we need to show that this relation, that you are given, is an equivalence relation. Okay, so first let origin is O, which is 0 comma 0. And that means if I try to write this R in easier manner, then R is all the set of points P comma Q such a way that OP is equal to OQ. This makes sense, right? Why? Distance of the point P from the origin, so that means OP, is same as the distance of the point Q from the origin. So OP equals OQ, right? And we took origin as O, which is at 0 comma 0. Now we need to show that this is equivalence relation. So we are going to start with reflexive. Now definition of reflexive is what? That we need to show that A comma A belongs to R for every A belongs to A. Now let P comma P belongs to R. So if P comma P belongs to R, that means we are taking A equals P. That means we are saying that OP is equal to OP. From this condition in that relation, that OP must be equal to OP, because we have taken P comma P as one of the element in that relation R. So yeah, of course, the distance from origin to point P is going to be same as the distance from origin to point P. So yeah, this is true, and that means we can say that it is true. So P comma P belongs to R, and that means A comma A belongs to R. As soon as we prove that A comma A belongs to R, R is reflexive. R is reflexive. Now we are going to check for symmetric. Now for symmetric, the definition says what? That if you have A comma B belongs to R, then you must have B comma A belongs to R. Now for this, let P comma Q belongs to R. Now if P comma Q belongs to R, that means from this we can say what? That OP is equal to OQ. That means distance of point P from origin is equal to distance from point Q from origin. Can I say other way around, that OQ is equal to OP? This means what? The distance of point Q from origin is equal to the distance from point P to origin. Of course, still the same thing, right? So this means Q comma P belongs to R. and that means B comma A belongs to R. And as soon as we prove that, it's symmetric, right? So R is symmetric. Now we are going to show transitive. Now definition of transitive is what? That if you have some A comma B belongs to R and you have B comma C belongs to R, then you must have A comma C belongs to R. So we are going to do let P comma Q belongs to R and Q comma S belongs to R. Now if P and Q belongs to R, that means from that condition OP equals OQ. That means if P comma Q is in R, that means OP must be equal to OQ. That means distance of point P from origin must be equal to distance of Q from the origin. So that means OP must be equal to OQ. Now if this point is also in R, so this implies that OQ is equal to OS. Distance of Q from origin is equal to the distance of point S from origin. So if you have OP equals OQ and if you have OQ equals OS, can't you say that OP is equal to OS? Of course you can, right? OP equals OQ, but OQ equals OS. So OP equals OS. And since OP is equal to OS, that means we can say that PS belongs to R. And that means A comma C belongs to R because P was our A and S was our C. So A and C. So AC belongs to R. As soon as we prove that, we can say that this is transitive as well, right? So R is transitive. Now, since it is transitive, it is symmetric and it is reflexive, we can say this is an equivalence relation. So we can say what? Hence, R is an equivalence relation. Now we had something else as well to show, right? So what was that question? Further show that the set of all points related to a point P which is not origin is the circle passing through point P with origin as center. So everywhere we talked about what? That there is a origin 0, 0 which is O and there is a point P. There is a point P and the distance of OP is equal to the distance of OQ. So Q is also somewhere such a way that distance from origin to Q is same as OP. You have somewhere S as well, which is again same distance as OP, same as OQ. So if you are going to keep on drawing that kind of lines, it is nothing but what? This path is going to create a circle. So it's going to create a circle with center with center O and radius is going to be OP and radius is going to be OP, right? That makes sense. Why? Because they were all along talking about the distance from origin and all those distances were same. All this distances OP is equal to OQ is equal to OS. If I write few more names for the other points, then those are all correct. Those are all same. And if they are all same and they are in the relation of just one point, see o, so every distance with origin is same. That means they are going to construct a path of a circle. So it's going to be circle and that OP is nothing but radius. So it's going to make a radius of that circle.
Okay, so that's it for today, and we'll solve remaining questions in the next video. Please remember to like and subscribe the video. See you all soon. Thank you.